Good afternoon, everybody. My name is Jerzy Barglik. I'm professor of the Silesian University of Technology. And today I have a pleasure to present induction surface hardening. That is the topic of my presentation. I start with a short introduction, then I'll concentrate on mathematical modeling of induction surface hardening. I spent some time on metallurgical aspects, including unbalanced diagrams, modified unbalanced diagrams, and the last part of my presentation will be concentrated on review of some practical application. So here is listed 5 such kind of practical application. First, 4 are results of research done in the Silesian University of Technology, in my university. And the last one, GeoWheels, it means it is a result of research activities all over the world, because it is very often done research investigation. And I finished with the small conclusions. I start with a short information about the Silesian University of Technology. I graduated this university in 1973. This university this year has 70th anniversary of founding. And I graduated, of course, electrical engineering faculty. Nowadays, I work for material science and metallurgy. And it is here in Poland, the second biggest technical university located in the strongly industrialized region, the Upper Silesia. And very shortly about my research activities. So I specialize in electrotechnology, electromagnetic processing of materials. So my topic of interest are surface induction hardening, which is the topic of the presentation, and also transverse flux induction heating to semi-liquid state, levitation melting, semi-levitation melting, new construction of induction furnaces, and at the beginning of my research activities, magnetohydrodynamic devices for transportation, steering, and purification of liquid metal. If we consider surface induction hardening, the process represents the most interesting, in my opinion, application of induction heating, making possible to achieve thin surface layer with different mechanical properties in comparison to the core of material which remain soft. And there are 3 stages of the process. First one, it is a fast heating, causing the layer to be hardened if the process is realized. So it would be necessary to heating by induction to temperature higher than the upper critical temperature. It is made possible to form uniform austenite structure. And in order to have a uniform austenite structure, it is necessary to heat to temperature higher than the upper critical temperature. It's called simply hardening temperature. And the second stage is a very short one, holding the body at this temperature for a short, but from other point of view, sufficient time in order to obtain a structural equilibrium in the regions. And the last stage is totally classical, fast quenching in order to receive stable martensite structure. And of course, the speed of cooling resulted in hardness, what is you seen at the picture. And the feature of surface induction hardening is the first possibility to localize treatment in a surface layer facing the inductor. So it could be a local treatment. And it is very easy to regulate, to influence on thickness of hardened layer. It depends on field current frequency, of non-power density, of course, on material property of treated material, and, of course, on heating time. And also very characteristic is big volumetric Joule losses, which could be achieved by using high frequency field currents and short heating times. Result is very thin hardened layer. And unfortunately, there is no general rules allowing to define optimal parameters of the induction hardening process. So, of course, distribution of eddy current in the treated body and optimal values of the heating time interval between end of heating and beginning of quenching velocity, there are parameters deciding about the process. Of course, there are many other factors. There is the reason that it is so difficult to find optimization criteria for the process, because besides on material properties, also important is shape of the body, presence of any kind of holes or edges, or thickness of layer, distance between inductor and workpiece, position of inductor edges, its dimensions, etc., etc. And of course, it is also possible to discuss and to decide about hardened profile. And nowadays, there is no problem, in fact, to elaborate models for numerical simulation, and such kind of model supported by well-planned experiment are good for prognosis of hardening profile. Characteristic is also that nowadays we could use inductors for induction heating before the treatment. We could use flux concentrators. And if we try to group the main factors influencing on the results of induction surface hardening process, first is steel grade and containing with that content of carbon, value and distribution of temperature, especially in the region to be hardened, speed of quenching, geometry of the inductor sprayer system, so arrangement and usage of inductor with flux concentrators. We will see at the next slide in a moment that content of carbon is decided for quality for percentage of martensite structure and decided about complete hardening. So still with carbon content between 0.2 to 0.6% are normally used. So it's more typical steel used for induction hardening processes. And you see you have here at the axis hardness in Rockwell degrees and carbon content. You will see that this martensite structure changes accordingly to carbon content. And it can be observed that the carbon content influence on the upper critical temperature, AC3. This is the temperature above it formation of austenite take place. It is not good quality picture, but I hope that you see the line AC3, which is changed with carbon content, and hardening temperature is slightly higher. Of course, it is not seen here at this picture. The value of upper critical temperature depends on rate of heating. Of course, there is some specific feature of this problem because there is very fast process, rapid induction heating, and hardening temperature must be increased above the AC3 shown in the figure in order to guarantee a minimum time interval above the temperature of austenite formation. I will come back to the topic later. And also influence of addition content of the critical temperature you will see here. So critical temperature increase for steel containing such kind of elements like carbides, titanium, silicon, molybdenum, vanadium, or tungsten. Of course, the hardening depths and the steel grade are given, and it is necessary to heat all points of the layer to be hardened to the temperature about AC3. And as I mentioned, or to higher values for rapid heating, while at the same time keeping to lower temperature internal layer, which should remain soft. This can be achieved with rapid heating and high or medium frequency field current. So there is low frequency are not applied for this purpose, of course, because of too big depth of electromagnetic field penetration. So this is only medium or high frequencies of field current. And of course, simulation are very good. We could consider many cases, many practical examples, but of course simulation should be verified by well-planned experiments. And here you see algorithm for the computation of the electromagnetic hardening problem. So we start with the electromagnetic field. Of course, material data should be updated. So I mean magnetic permeability, which depend on induction flux density, on temperature, and also on field current frequency. Three factors influence it. And then you see here that is induction flux density change, so there is a magnetic permeability is modified. And then you calculate non-stationary temperature field and heat stress field, and all these parameters are modified with changing of temperature. In a short period of natural cooling, we calculate non-stationary temperature field only, and then we have quenching, we have intensive cooling here, so we calculate here non-stationary temperature field and heat stresses field. And finally, we have metallurgical field, we have parameters of hardness and structure, and it is fully based on experimental data. And the result is hardness and microstructure. So it is very complicated algorithm. In many cases, a lot of simplifications should be introduced. As an electromagnetic field, classical basic equation are applied. It is equation for magnetic vector potential. Of course, a term with velocity should be neglected. And we could consider any part of the system as with constant magnetic permeability. We should use equation for phasor of magnetic vector potentials. Here, of course, it is an angular frequency, omega, mi, magnetic permeability, and gamma, it is an electric conductivity. Of course, Jx, it is field current density. And of course, classical boundary were applied, so it had external border and the sufficient distance to the system, A is equal to 0, and also at symmetry plane, the next equation should be satisfied. And in case of 2D formulation, of course, it is the first derivative of normal is equal to 0. And normally is velocity of movement, of body movement could be neglected, so eddy current density and volumetric Joule losses are written here. And of course, if we compare losses connected with eddy currents and connected with hysteresis, these losses connected with hysteresis could be neglected. And in case of 3D formulation, we used TC formulation with the electric vector potential and scalar magnetic potential and magnetic field strength is calculated directly from the Biot-Savart law. And this is, of course, a simplified method, but is used in majority of professional software packages applied for the purpose. And of course, temperature field here. I would like to tell something about boundary condition, because equation is typical one. So it is necessary to take into consideration not only convection, but also radiation. From my research activities and my investigation, I'm sure that it is necessary. Of course, we should calculate general convection heat transfer coefficient, but of course it is a kind of simplification again. And stress field is written by equation shown here. So here is Young modulus and viscosity coefficient, and of course here is add volumetric magnetic force, which volumetric density is a vector product of current density and induction flux density. And very important is temperature dependence on velocity during cooling. It depends on many factors, and in fact it is possible to use any kind of quenchmeters which could make possible to calculate real value of convection heat transfer coefficient. And more complex problem is connected with relative magnetic permeability. Here I show dependence only on magnetic flux density, left diagram, and temperature. But of course, if we use field current density of bigger frequencies, we should also have the third diagram showing dependence of relative magnetic permeability on frequency. Other material properties are also should be measured, and there is a less problematic task, so it is not difficult. It could be done in any kind of physical laboratory very easily. And of course, also very important is final structure and on the initial microstructure influence of final structure and hardness distribution after the process. And if we, for good computer simulation, it is necessary to know time, temperature, oscillation diagram. So if you look to the references, you have the classical, conventional TTA diagram, which is different from this one. This is realized by dilatometric measurement. So have you seen here, it is done for steel 41 chromium 4, and heating was to temperature 1050 centigrades, and when the heating rate is about 100 centigrade per second, so AC3 increase of about 150 centigrades. So it is necessary to know what kind of temperature should be final after induction heating. And of course, for each kind of steel, such kind of measurement should be done in order to be sure that before the process you have a good austenite structure. And the same is done with the time temperature cooling diagram. So it also differs from the classical conventional diagram shown from industry, shown from the physical tables for the material. So here you have austenization time is 2 seconds and temperature 50 centigrades. Based upon that, this characteristic dependence of hardness on speed of cooling could be elaborated. And of course, we should have complete hardening for if cooling rates higher or equal to critical one, or we have residual austenite if the steel is highly alloyed. We have here so-called complete hardening. In opposite, we have incomplete hardening when the martensite is a hard and brittle constituent whose hardness is higher, the highest content of carbon, and cooling rates lower than critical one, and we have incomplete hardening, which means martensite with mixture of bainite and also ferrite, sometimes, or ferrite even. Of course, if we have continual induction hardening, the problem is more difficult. It requires another type of algorithm analysis because it is very difficult to introduce a term connected with velocity. The simplest way to do that is divide the body into sub-regions, and we have input data, start, we calculate electromagnetic field for this start position, and then temperature field. We collect database for further hardness distribution, and if the position is not final, it is position 1, for instance, we repeat the computation for next position, and after that, after a moment when the inductor reaches the final position shown here on the picture right, we stop the calculation and it is a termination of field calculation, and we have determination of hardness and process terminated. Of course, there are many books, many references shown some experimental diagrams facilitating this designing of process. However, nowadays, the majority of analyses were done by numerical methods. Another problem was selection, was choice of quenchant. So, of course, it is basic quenchant is water. Sometimes often is used oil, but nowadays more often used synthetic polymers, fluids or solutions. And of course, speed of quenching strongly depends on kind of quenchant, so it should be taken into account during simulation. And another strong problem is internal stresses. There is a reason that Martensite transformation causes a volume increase. So if the process is too fast or transformation is irregular, it is induced substantial internal stresses which may cause deformations and cracks, especially in the case of complex geometries like geowheels, but some other as well. And also temperature differences between the quenching curves on the surface layer and these one putting at the core where cools down slower increase with high quenching rates. It is natural that it causes expansion of the internal mass against the hardened surface layer and a higher internal residual stress with the possibility of workpiece distortion and formation of cracks. The similar problem also is when we quenched by spraying. So there is a reason use lower quenching rates. So of course it depends of resulting hardness. So this process should be analyzed during simulation. Yes. And nowadays I would like to describe a few examples of practical cases of induction surface hardening. The first one I think is interesting one because it means induction hardening of internal surfaces of steel tubes. So we are in Poland, we have a lot of underground hard coal mines. So there is a problem of steel tubes production for transportation, mixture of loose materials, mixture of sand and water in order to have highly mechanically resistance and respect to abrasion. And it could be, of course, done in two different ways. Of course, the distance is, let's say, a couple of kilometers for transportation, and tubes are 2 meters long, so they should be hardened its internal surface. It could be done by external inductor, like here you have it, and by right picture, and by internal inductor. And of course, in case of external inductor, there is a danger that the region when you weld in order to join tube into tube line, you should reduce the hardness, tempering, and it could be, better to use internal inductor. And the electromagnetic model, fully axi-symmetric, is shown here. It is also could be done, it is 2-meter long tube, so it should be divided into a number of steps. So it is changed by shifts, and it is, in that case, it was divided into 200 steps, 200 shifts. And so the algorithm is very similar to this one describing myself earlier, so I do not stop at it. Of course, we should control material properties and their temperature dependence and as usual. And we have time evolution here on the bottom points on time, and after that we should calculate the hardness. So we use it for that. I use it for that with my group continual induction hardening program. So this is a program elaborated by our team and done among the Polish-Czech collaboration group. So this is a result of collaboration between our university and University of West Bohemian University in Pilsen, Czech Republic. And quite good results were achieved, quite good accordance between simulation and measurement done on the experimental stand. Of course, there is one important problem here. We have 2 meters long tube, and you should move the tube from the lower position to higher position. You should have 2 meters long bus bars. So it is a problem of optimization, how it would be arranged, because losses in this bus bar should be also taken into consideration. The next, also interesting and patented by my team solution, is induction hardening of conical mandrels. It is used for in the process of tube production, and you have here moving inductor, spraying quenchant, hardening steel querpiece and cool part, and it is cooled by moving sprayer. So it is a conical, it is not cylinder, so there is a special kind of inductor should be applied. Inductor is cylindrical, and of course for that it is also similar continual induction hardening software was used. So we constructed model here with parameters. We introduced material data, and calculation were done by this software. We have here input data, dimensions of mandrel, of coil, of current density, of field current frequency. Velocity movement is rather slow. It is only 2 millimeters per second. And we have result. It is a time evolution of the temperature at selected points. And finally, we have hardness distribution along the mandrel. So it is a quite high, requested quite high in hardness. So this part is only important because in this part only this part practically applied in the process here. And next example, next case is steel section for plastic working. It is used, it is also 1 meter, it is also long element shown here in cross section at inductor hardened this this surface shown here. And of course you will see here 3D arrangement. So axial length of the body is about 118 centimeters, and of course inductor moved with small velocity. And of course we have it here again, time evolution of temperature selective points, and based upon some curves we could elaborate, we could calculate the hardness distribution, and also all these three examples, three illustrative examples are practically introduced to different Polish companies for production. And this is also next example. It is circular saw. This saw is used for cutting of iron material. It is made from typical Polish carbon steel, and it is used for cutting of, in practical cutting for continual cast in steel plants. It is analysis was done in the system shown here. So it is extremely important hardness in this region near 0.3, and parameter, this field current is almost 1000 ampere, 850, and frequency is 40 kilohertz, and parameters AC3 is 780 centigrades for this kind of steel. And you will see here calculated temperature distribution. So it is done that temperature below 780 centigrades is shown in the area of 3. So it could cause good hardness distribution. So this part of this saw is fully hardened. And finally, I would like to concentrate shortly on gear wheels. It is a more typical hardening example with complex geometry, and as I mentioned in the beginning of my presentation, I concentrated here not only on my research activities, but also about the state of art in in references. So influence on frequency of field current frequency of on temperature is shown here. So you will see that if you have frequency 100 kilohertz, you have here temperature more than 1000 centigrade. And you have here for such kind of simultaneous contour hardening parameters, where here we have module of gear wheel and calculated optimal Joule losses, optimal power of generator, frequency, and heating time. Yes, of course it is, there are different patterns received during induction surface hardening of gear wheel. The best pattern is usually, of course, a uniform thickness of the hardened layer along the contour. But, of course, it could be very different patterns. I have no enough time to discuss details. What kind of parameters deciding about this pattern? I mentioned about it at the beginning of my presentation. It is, of course, field current frequency, power density, heating time, quenching condition, geometry of the system, kind of treatment, kind of surface induction hardening, or single frequency or dual frequency process. And of course, if we look at it, consider spin hardening methods, we should think about through hardening, which is very not often applied, and contour hardening by single frequency or by dual frequency with preheating or with pretreatment. And of course, it could be also done simultaneous process, which is very good, but not very easy to do. And after that, for gear wheels, is absolutely necessary. It is very important to apply immediate tempering, which could be induction or classical one, but it should be done immediately in order to avoid stresses. If we think about single frequency process, spin hardening, all teeth are simultaneously hardened by means of single frequency inductor. This is a cylindrical inductor. It requires usage of high induced power densities and very short heating time. The reason is very simple. We should avoid diffusion of heat from the surface layer to the lower material and the consequent through hardening of the teeth. And we have here a calculation example, heating by medium frequency, 10 kilohertz, and by high frequency, 500 kilohertz, and you will see the distribution of temperature within the hardening layer. And if we look about optimal parameters, so at the beginning we should use very simple formula. So optimal frequency depends on square of module square, and you will see also dependence of specific surface power, heating time, and frequency on module of the gear wheel. And of course, there are different possible conditions of heat treatment. So we could start with preheating the temperature to about 500 centigrade by medium frequency, and to higher temperature by high frequency field current. And we have hardness, received hardness profile with preheating or with pre-quenching and tempering, so you could compare these photos. And of course, dual frequency hardening. The use of two frequencies is the logical solution for obtaining a uniform hardening depth along the contour. Of course, there is one important limitation, diameter. So it is used rather for low diameters. The biggest is 250 millimeters, but normally it is used for smaller ones. Of course, one example of dual frequency cycle, we have here preheating with medium frequency, and then contour hardening with high frequency. Of course, in order to avoid through heating, the final austenization operation must be very short. So it is necessary to have a source of high power. Oftentimes less than 1 second. It is necessary to have very fast transfer of the workpiece from one inductor to another, and very high power switching speeds, which is decided for quality of the process. Of course, the best way, as I mentioned at the diagram shown a few slides before, that the best system is one inductor only. And of course, it is almost 1 hour, so I would like to slowly go to the end of my presentation. So finally, I show you dual frequency hardening stent installed in my university, where it is possible to provide experiments before introduction, before implementation to industry. And I finished my presentation with some conclusions. So, surface induction hardening has provided two distinct improvement of quality of steel element. It is characterized by fast heating and immediate quenching. Heating depths can be easily changed by field current frequency, power, and heating time. And numerical simulation seems to be a powered tool, but only tool supporting effective implementation of the process to industry, because if I may to add something to this conclusion, the main problem, main disadvantage in implementation of induction hardening technology to industry is a necessity for long-term experiments. And the fifth conclusion, fifth sentence, energy efficiency is an important factor deciding about practical implementation of the surface induction hardening. We compare carbonizing with induction surface hardening. It is evidence that it is even difficult to compare if we tell about energy efficiency. And I would like to tell that the presentation was elaborated within the framework of the ongoing Polish grant, sponsored by Polish Center for Research and Development, and also some parts were prepared for my PhD students during in a framework of Tempus project, energy efficiency technologies for in electrotechnologies, which will be provided for Russian students in Samara, Krasnoyarsk, Petersburg, and Novosibirsk in English. So, thank you for your kind attention.